Wheat that once collapsed under heavy grain now yields 2 to 3 times more per acre because breeders shortened the stalk instead of adding still more fertilizer. This is First Principles Daily, episode 59. For centuries, a wheat plant that received extra nitrogen simply grew taller until its own weight toppled it flat in the field. Norman Borlaug and his colleagues refused to accept that limit. They asked what fraction of the plant's fixed energy was being spent on scaffolding that delivered no grain. Then they bred varieties that spent almost none of it there. The result was a plant whose finished output moved measurably closer to the theoretical ceiling set by sunlight, water, and soil nutrients. Farmers had long treated lodging as an unavoidable cost of richer soil. When manure or later synthetic nitrogen made heads heavier, the tall stems that had been selected over generations simply bent or snapped. The standard response was to hold back on fertilizer so the crop would stay upright, or to accept the loss when storms arrived. That habit traced back to the land races farmers had saved for centuries, each chosen because it performed adequately under the low nutrient conditions of its own field. No one had started from the plant's energy ledger and asked how much of the season's photosynthesis could be redirected once the stem no longer needed to support several extra feet of height. The convention therefore locked yields near the level that tall straw could physically carry. In practice, that meant roughly 750 to 1,200 kilograms of grain per hectare on the better Mexican plots before the 1940s, even when water was adequate. The same ceiling appeared wherever farmers tried to intensify without changing the plant itself. Breeders outside the program continued to select for visible traits such as disease resistance or earlier ripening. They left the stem length and stiffness largely untouched because those traits had always been good enough. The result was a stable but low ceiling that felt natural inside the profession. The energy budget inside any wheat plant is set by how much light its leaves capture and how the resulting carbohydrates are partitioned between roots, stems, leaves, and seeds. Tall landraces had evolved under nutrient-poor conditions where extra height helped them compete for light. Yet the same height became a liability once nitrogen supply rose, because each additional centimeter of stem required lignin, cellulose, and vascular tissue. The plant diverted grams of carbohydrate that could otherwise have filled more kernels. Farmers and breeders accepted this diversion because no one had measured the exact split between structural and reproductive biomass under the new fertility levels. They simply observed that the plants fell over and concluded that more fertilizer would make the problem worse, rather than asking whether the stem itself could be shortened. That conclusion became self-reinforcing. Seeds saved from the previous harvest carried the same tall straw genes. Any short mutant that appeared by chance was usually discarded because it looked weak or low yielding in the low nitrogen trials that were the norm at the time. Borlaug began with the observation that the plant's total photosynthetic output was fixed for a given field and season. Any gram of carbohydrate directed into stem tissue was unavailable for the seed head. The magic wand floor would be a plant that produced only the minimum structural tissue required to hold ripe grain above the ground, and then poured every remaining gram into starch and protein. Under that accounting, the conventional tall wheats carried an idiot index of roughly 3 to 4. They spent 2 to 3 times more carbohydrate on non-grain tissue than the physics of light capture and grain filling strictly required. The first concrete redesign step was to import the short, stiff straw of the Japanese Norin 10 variety. Its reduced height had already been noticed by U.S. Department of Agriculture observers. Crosses were made with locally adapted Mexican lines that carried good rust resistance and yield potential under irrigation. Early selections still lodged because the dwarfing genes interacted poorly with the background genome. So the team repeated the cycle, each time measuring stem strength directly under high nitrogen plots, rather than under the low fertility conditions that had shaped older varieties. A second move was the shuttle breeding system itself. Seed was advanced 2 generations per year by sending material from the mild winter environment of Ciudad Obregón in Sonora to the cooler, longer day summer station at Chapingo or Toluca. That compressed the calendar so that 10 generations of selection could be completed in 5 years instead of 10. Each generation was grown at deliberately high fertility so that lodging pressure remained constant. Any line that fell over was discarded, regardless of its other merits. A third step was simultaneous selection for shorter internodes and thicker stem walls rather than simple height reduction. A thin, short stem could still buckle. Breeders therefore scored both final height and the diameter and lignin content of the culm on the same plants. A fourth adjustment addressed the new disease pressures that appeared once the canopy stayed dense and upright. Genes for resistance to stem rust and leaf rust were pyramided into the same short straw backgrounds so that the extra leaf area did not become a liability. Each of these moves reduced the fraction of total biomass that ended up in non-reproductive tissue. They moved the effective idiot index downward. The key engineering trade-off at every stage was that the new plant required reliable water and nitrogen to express its higher grain fraction. Without those inputs, the dwarf lines yielded no better than the old tall ones. One objection often raised is that shortening the stem must reduce total biomass and therefore total yield. In reality, the total above-ground biomass stayed roughly the same while the proportion allocated to grain rose sharply. The plant still captured the same amount of light. It simply stopped building excess stem that would later be lost to lodging. Another concern is that shorter plants might shade one another less effectively. Yet the upright canopy actually allowed more light to reach lower leaves and increased the number of productive tillers per square meter. The shuttle breeding method succeeded because it kept the selection pressure constant across environments. Lines that performed only in one location were eliminated before they could waste further generations. By measuring stem diameter and lignin alongside height, the team avoided the trap of selecting merely for shortness without mechanical strength, a mistake that would have produced plants unable to stand even at moderate wind speeds. By the mid-1960s, the best dwarf selections were delivering roughly 3,000 to 4,000 kilograms per hectare under the same irrigation and nitrogen regimes that had previously supported only 1,000 kilograms. In India and Pakistan, the same varieties, once multiplied and distributed, lifted national wheat output several-fold within a decade. The new idiot index, measured as non-grain biomass relative to the theoretical minimum needed for support, had fallen to something closer to 1.5. It was still above the absolute floor but far below the earlier ratio. The remaining gap sits in the continued need for structural tissue to resist wind and for root mass to extract water and nutrients. The redesign also increased dependence on consistent irrigation and on the steady supply of nitrogen fertilizer. So any break in those inputs collapses the yield advantage. Monoculture of a narrow set of varieties created new vulnerability to evolving pathogens, a risk that still requires ongoing breeding vigilance. Those limits are physical and logistical rather than failures of the original reasoning. The higher grain fraction also meant that more of the plant's nitrogen uptake ended up in the harvested grain rather than in the straw left in the field. This shift improved nitrogen use efficiency on a per kilogram of grain basis, yet it simultaneously raised the absolute requirement for applied fertilizer, because the crop now removed more nitrogen from the soil each season. In regions where irrigation infrastructure was already in place, the yield jump paid for the added inputs many times over. Where water or fertilizer delivery remained unreliable, the advantage shrank or disappeared. Pathogen evolution remains an ongoing cost because a single successful rust race can overcome multiple resistance genes at once. It forces breeders to maintain a pipeline of new gene combinations rather than a one-time fix. A crop whose stem once consumed half its energy budget reveals how much of any finished product can be scaffolding that no longer serves the goal once the goal is stated in raw energy terms. The same ledger that made tall wheat look inevitable also made the dwarf solution obvious once someone measured the allocation instead of copying the previous year's seed. Tomorrow the show returns with another concrete case or an industry still operating far from its physical floor. The question is, which daily object around you is still built on the assumption that yesterday's height was necessary? That's first principles daily for today. If this changed how you see what things cost, share it with someone who'd appreciate it and subscribe wherever you listen. I'm Patrick in Vancouver, one example or one opportunity every day. See you tomorrow, and if you'd rather watch than listen, find us on YouTube at Nerra Network. Links in the show notes. One more thing, if you like today's episode, our sister show, Planetarian Daily, is worth a spot in your feed. Daily breakthroughs in science, health, and longevity. It's one of the Nerra Network's daily briefings, all free at nerranetwork.com. Prefer reading? Today's full write-up, sources, and transcript are on the episode blog at nerranetwork.com. Same briefing, readable format. This episode used AI voice synthesis of my voice. Editorial selection and analysis are my own. I'm about to prove